Hey, this is Horner, and this is electricity worksheet and we're going to look at problem number 4. You'll notice that this is a parallel circuit, and with parallel circuits, we're going to use something called the junction rule. So in the last video, we did number 3, that was a series circuit, and in that one, we used the loop rule. We said that anytime you go through a loop, you should have the voltage, if you add the voltage at the battery plus what is dissipated by the resistor, then that should equal 0. So we'll take a look at that a little bit in here, but this one is primarily about using current junctions. So a junction is kind of like if this was a highway. When I get to this point right here, this would be a junction. And at that junction, we know that the electricity can go straight through, we can go left or go up here in this case, or we can go right or down. Then it'll come around and then it will come back out. So it's going to go this way to this junction and then it'll come back out. And the key here is whatever the current is that's going in. So for example, if this is 5 amps going in here, then the sum of these three must equal 5 amps. So this might be 2 amps, this might be 2 amps here, and this might be 1 amp. And then as it goes through, as it comes back in, it needs to equal that 5 amps on the other side. So when you put an ammeter right here, and it measures 5 amps, we know that on the other side of the battery, it should also equal 5 amps. This is also a good place to talk about what is an amp. An amp is really just the flow of charges going through the wire. And 5 amps would be the same thing as 5 coulombs per second. If we think about water, it'd be like maybe the water is going 5 meters per second here. And then as it divides inside, this water would be going 2 meters per second, 2 meters per second, and 1 meter per second. And then the water gets back to the junction and it comes out the other side, it'd be going 5 meters per second again. That's basically what current is and kind of what that would look like if we were thinking about what's going on. So that is the junction rule, or Kirchhoff's junction rule. Next thing that we need to do, and I need to clear all this off here really quick, is we want to go through and we want to actually solve the chart that we have over here for our circuit. In the end, we're looking for power in each one of these resistors. And to do that, we're going to use the chart just like we did in the other problem. You'll notice though that this one doesn't have a place for us to go through and figure out what is the voltage that would then make a 0 voltage in the end. So because this is a parallel circuit, we're going to see that all of the values for voltage is going to be the same. And since this is the only part of the circuit, we know that the voltage in this entire thing will be 12. So I'm going to get rid of those double dots there. So we know that everywhere in the circuit, the voltage is going to be 12 because this is a parallel circuit. Let's go ahead and put in R15. And then here we have R10, and finally we have resistor 6. And we'll put in our resistances. So this is 15, this is 10, and this is 6. If you remember earlier, we went through and we had 12, 4, and 6. Now we have 15, 10, and 6. The voltage in each one of these is going to be the same. So we can go ahead and write in the voltage for each one. So these are all 12. The resistances in this one, we can't just do the sum. Remember, we have to do 1 over the total resistance, or 1 over the resistance in parallel is equal to 1 over the first one plus 1 over the second plus 1 over the third. So down here I'm going to write that 1 over the resistance in parallel is equal to 1 over 15 plus 1 over 10 plus 1 over 6. If you put these in parentheses and enter it in your calculator that way, it will come out correctly. And then you will end up with a value for 1 over Rp. And the value that we get for 1 over Rp is 0.3333 repeating. So remember, we can't say that this is the resistance. Instead, we have to do the inverse of this number and the inverse of this side so that we actually solve for the resistance in parallel. And 1 divided by 0.3333 is going to give us 3. So that is our overall resistance. And we now can put that in this spot. We can go ahead and put let's go ahead and put the symbol there. So now I know that this is 3, this is 12, and I can now go through and for each one of these I can find out what the current is. In a series circuit, all the current were the same. In a parallel circuit, all the voltages are the same. So because we have current junctions and we know that the current coming into the circuit needs to equal, into the junction needs to equal the current of the branches added together, let's figure out what these three are. So let's go ahead and take 12 divided by 15, 12 divided by 10, and 12 divided by 6. So this is 2. This will end up being 1.2. And then our top one is 12 divided by 15, which is 0.8. So this one is 0.8. We know that 12 divided by 3 should be equal to 4. And if I add 1.2 and 8, I get 2 plus 2 is 4. So everything is worked out really well now. If I want to, I'm going to go over here and I want to write in not the voltages because I know what the voltage is for each one. It's 12. This time I would like to go in and I want to write in what is the current for each one. So for the 15 ohm, I get a 0.8 amp current. For the 10 ohm, I have a 1.2 amp current. And then finally for the 6 ohm, I end up with a 2 amp current going through it. The power for each one, if you only have the current and the resistance, you can solve. So I can take 0.8 squared times 15, or I can just use IV again. So I can take my voltage times my current. So let's go ahead and find out what the power is in each one of the resistors. So I now have those values for power. I have 9.6 watts, that's 12 times 0.8, or 0.8 squared times 15. I have 12 times 1.2 is 14.4 watts, and then 12 times 2 is 24. If I add these up, it should equal the voltage times the current in the total circuit. So 12 times 4 would be 48, and if you add these up, you'll see that you also get exactly 48. So let's put the power in. We know the power in the entire circuit is going to be 48 watts. We also know that over here, that in the 15, we get 9.6 watts. We know in the 10 ohm, we're going to get 14.4 watts. And then finally, in the 6 ohm, we're going to end up with 24 watts. So we know the power in each one of these. Now that we have the power in each one and we know the total power in the circuit, we're essentially done. Let's go back to bulb brightness again, and let's notice that the 15 ohm bulb here is the dimmest bulb. So this one is the least bright. So we're going to put the least bright, or its brightness is low. We also know that this one is going to have a medium brightness, and this one is going to be the brightest, or it has a very high value for how bright it is. And that is a parallel circuit, and that is using the current junctions by Kirchhoff.